Hello, welcome, and if you are watching this recorded, which you probably are, then you aren't subbed up, so make sure that you are subbed up to see them when I do lives like this. I'm going to do live tonight and tomorrow night because this week is the papers for GCSEs and for the triple science physics as well. So if you're just arriving, can you give me a thumbs up? This is nice and clear and you can make out the paper. There's a bit of high contrast over there actually, so I'm going to move my camera just ever so slightly because there's so much light streaming in on this gorgeous day. You're all probably revising. These are higher tier questions, okay? I'm going to whiz through them and I will stop if you've got any questions after the multiple choice and after any of the longer ones, okay, and at the end of it, and if I'm going to do a Q&A at the end of it as well. Hello everybody and welcome. If you're an A-level student, then you should be jetting over now to A-level Physics Online because Lewis is doing a live feed for that tonight as well. I will do A-level live feeds as well on the run up to that exam. This is for OCR specifically, but also if you're an AQA student, then in the links down below, there is AQA full Paper 1 exam playlist. And there's also a full OCR exam playlist as well for you to use after this as well. That's going through another specimen paper. Okay, so I'm going to get right into it now. Ask questions just as and when, but I'll review them. I'll just have a little look over them at the end of a couple of sections, if that's okay with you. And then if there are questions for things you'd like me to go through, anything at all, then I'll do that briefly afterwards as well. Actually, this one was in my previous video, which sort of surprised me because the answers are different down here, and I think they've got the answers wrong for this one, but let's go through it as well, just talk to what we're going at. So you've got to compare to y, so that's y, and this is x. And you've got to talk about the strength and the direction, okay? So the magnetic field of x is actually stronger, I think, so straight away I can see it's not any of these answers. So they've definitely made a mistake here. Certainly the closer you are to a current carrying wire, the stronger the field is. So the field will be stronger at x, and it would be the opposite direction, because if the current was going up and you're not told this, then the current would be going around that by the right-hand grip rule. So the current would be going down here, sorry, the magnetic field will be going down here, so therefore up here, okay? So I hope that makes sense. This would be none of the above, but I'm sure in the real thing they won't make an error like that. It's a pretty straightforward error. This one, you give them some information and you ask to deduce what component this is. Okay, the unknown component normally has got an ammeter reading of 1 amp, and the connections are reversed and the ammeter reading is suddenly 0. So what is this? Well, it must be a diode, because diodes only work in one direction, so nice and easy for that one. Okay. The two forces act on an object in equilibrium. Which one of these statements correctly describes them? Okay, so when you do this, just read through and make sure you're looking for the correct one in this case. They're different in size but have the same direction. No, that would add up to a resultant force, not an object in equilibrium. That's what we're looking for. They're different in size, it can't be in equilibrium really, can it? But have opposite directions, closer but not correct. They're equal in size but have the same direction. No, that's not correct. They're equal in size but have opposite directions. D. So the answer is D here. So this is an example: two equal size opposite direction forces and the forces sum to 0. The resultant force is 0. Easy peasy. Complete the sentence. A constant resultant force acting on an object cannot change the object's acceleration, kinetic energy, momentum and velocity. So when you first see this, then you can be forgiven for thinking that actually none of these above. Surely resultant force causes an acceleration. Surely a resultant force increases the velocity and therefore would increase the kinetic energy. Increases the velocity, therefore increases the momentum and increases the velocity. There's an acceleration. Ah, right. A constant resultant force cannot change the object's acceleration. A resultant force is equal to a mass times acceleration. So although it causes an acceleration, it doesn't change it as time goes on. Okay, so that is why that was question A. Tricky one. Okay, a beaker contains water with a mass of 540 grams. Specific latent heat with vaporization is this: 2.26 times 10 to the 6 joules per kilogram. How much energy is needed? So you've gone to your equation sheet and you select that one. You don't have to remember that one. Energy is mass times specific latent heat. But you can see in here the units are joules per kilogram. So you've got to convert this to kilograms first. And there's not a mark for this because it's a multiple choice one. Then it's a matter of plugging that into the calculator, and the calculator reads off all this. So just figure out all the same numbers. That makes sense. But which standard form is it? Okay, so how many times you have to move this decimal place? 6 times, so the answer is B. Okay, I hope that makes sense. Next one, circuit components. This one is, well, straight away you recognise it's a lamp, I hope. Okay, potential difference, current in the positive and negative, right? So which row has the correct statements for this type of lamp? So resistance decreases, temperature increases. No, that doesn't make sense to me, okay? Hotter things have a higher resistance, so neither of these do. It's got to be one of these two, hotter things, higher resistance, because, well, they're rubbing together, friction causes vibrations, therefore the resistance increases. So it's got to be one of these two. And the current, is it directly proportional? No, it's not directly proportional. Directly proportional will be a straight line through the origin. This one is not, so the answer has to be D. Okay, a ball has a kinetic energy of 100 joules. The speed of the ball is doubled. What will its kinetic energy be? Well, the kinetic energy, if we double the speed, then we get a factor of 4 for kinetic energy because V is squared in this equation. So, in other words, 100 joules, double the speed, you get 400 joules out. So that's D. Okay, that makes sense. Here we go. This one is quite a tricky calculation. This is the kind of two-step calculations that you have to learn to do. Okay, so a car and driver with a total mass of 1,000 kilograms is traveling at 20 meters per second. The driver applies the brake and the car comes to a stop in 4 seconds. What's the mean force? So my first thought was, well, F equals ma. What's the mean force? But I don't have, I've got a mass. Yep, that's mass there. I've got a speed and a time, but I don't have an acceleration. So what I would then do is go ahead and do a acceleration. So recall A is delta V over T. Delta V is the change in speed from 20 to a stop. So V 20 minus 0, in other words. So delta V, change in velocity, is 20 over 4 seconds. 5 meters per second squared is the acceleration. Then force is mass times acceleration and 5,000 newtons. Hope that makes sense. You could, of course, go ahead and use this as Newton's second law in the form delta P over T, which would have been just that times that on the top line divided by that. Okay, so I'll just do that really quickly if you don't mind. Delta P being the change in momentum over T, so it becomes mv over T. All right, or delta mv over T. Okay, hope that makes sense. Current in 12 ohm resistor is 9 amps. How much charge flows in 2 minutes? Now here, they've given you this as a bit of a herring because you don't really need to use that at all. You just need to recall the equation. Charge is current times time, okay? Or a lot of people, I actually remember it as being current is a charge flow over a time. That's the way that I remember this because it defines current for me. But you're not asked to work that out, so it's nice and useful. That's the way it's given in all the textbooks and everything like that. So you recognise 9 amps. Times the time button, you've recognised 2 minutes, so you need to think about that in seconds. So if you did it as 2, then you're going to be struggling to get this answer. So the answer is 1080, okay, so C. That's just what the calculator tells you. A piece of metal has a volume this, and a density of this. What's its mass? So you recall density is mass over volume, rearrange for mass. Mass is density times volume, put all the numbers in and plug all the numbers into the calculator. I'm just going to do this one on the calculator just to make sure you all understand the use of this button here. Okay, so 8 times 10 to the 3 times 2 times 10 to the minus 5. Okay, make sure you can use that, get it in that and convert. All of these are in standard form anyway, so you just need to think about, well, how many times does the decimal place need to move in that direction in this case? Well, it's that one, so it's just 1, it's minus 1 if it's gone that way. Okay, right, that's all of the multiple choice. Let's have a really quick look at the chat. Is there anything else that you want to ask just quickly now? And do. In year 10, but you don't have a video on Half-Life. I really don't. I'm sure I do have a video on Half-Life somewhere in my back catalogue. Just type in Half-Life Guerrilla Physics and see if there's anything up there. There's at least going to be some questions that are going to talk you through that. Half-Life for OCR radioactivity is in paper 2, so when it comes to paper 2 I can go through that in a live feed another time. Okay, I hope that helps. I don't think there's any other questions, just some kind of nice pleasantries and things like that, nice thumbs up. Okay, let's go on for the written stuff, and then I can ask if you've got any questions to go through in a kind of Q&A just after that. Okay, so some small piece of paper on a surface and negative charge rod is held near them. State what is meant by the term negatively charged. Now, there's going to be like so many of you thinking, okay, this is quite a difficult thing to describe. What does charge mean? Charge is an intrinsic property of matter. That's a difficult thing to describe. Matter just has charge. It is a thing that we have to just get used to. There's no way to really kind of say exactly what it is. It is. So we just have to take for it. So a lot of people are going to overthink this one. Okay, what's meant by the term negatively charged? Well, something has gained electrons, and that's all you really need to say. So overall negative charge, it's got too many electrons on there. It's all you really need to recognise. It's become negatively charged, so it's got extra electrons. So that's really all we're looking for. A negatively charged rod is made of another type of plastic, is brought near to the piece of paper. Why is the plastic rod able to keep a negative charge? It's because the charge cannot flow off it. Okay, or in other words, it's an insulator, is all we're really looking for. That one there. Explain why the piece of paper moved towards the charged rod. So this is the point. Why do charged things attract uncharged things? Well, actually, the charged thing gives the uncharged thing a charge. Okay, so because the charged rod repels the electrons, so actually in this little piece of paper here, the electrons move further away from the rod because they're repelled from it. So we actually get a positive charge at this end of the bit of paper, and that is the opposites that attract, so that you get an attraction. Okay, so the 3 marks are basically that one end becomes charged, or the charged rod repels the electrons, or induces a charge is one way that they've put that, causing the top of the paper to become positive, which is opposite, so you get attraction. Okay, next one, the diagram shows an electromagnet used to pick up some scrap steel. Here's a quality written communication one. It's worth 6 marks, but they're not all going to be worth 6 marks. So do make sure that you recognise the asterisks and pause and plan. Structure your answer. Okay, there's a really important thing about this. So explain so basically it's an electromagnet in a scrapyard. All right. When the switch is closed, the scrap steel is attracted to the electromagnet. Explain why this happens and what can be done to the apparatus to pick up even more steel. So really, they've told you the structure they're kind of expecting. We're expecting you to explain how an electromagnet works, and we're expecting you to give me some improvements to the apparatus. So basically, first paragraph, second paragraph. You might want to think before you write, just think about some little things here. But I've just done it in 2 paragraphs here. So I'll just go through this one here and think about the kind of answers for you here. When the switch is closed, the current flows through the wire of the solenoid. Okay, so first thing to talk about, switch closed, current through the solenoid. If you don't know, a solenoid is a coil of wire. Okay, mark there. A current has a magnetic field around it, so a magnetic field is set up within the solenoid. Mark there. I've said it's the same shape of a bar magnet, but I'm not sure you really need to in this case, but I've done that. The reason for the iron core is the iron core becomes an induced magnet in this field. Okay, so that kind of amplifies the field. Now, I'm probably only going to get 3 marks for that first little bit there, but I have added, when the switch is open, the core demagnetized and the electromagnet can drop the steel. It's just my extra thing about this idea of why would we use an electromagnet in a scrapyard. Don't necessarily need that for the mark. You don't, in these types of questions, when you look at these mark schemes, you don't need to say all the stuff in the mark scheme. You just need to have a well-structured, well-written, detailed response. So to pick up more steel, you could increase the current, and this would set up a stronger magnetic field. Now, I've got an idea, and I've got a reason why it would improve the electromagnet, and that's what we're looking for in the second paragraph, is you linking what you do, why it improves the electromagnet. You could also have more turns on the coil of wire, as this would link the magnetic field, making it stronger. So I'd probably get that mark just for more turns, but it's nice that I've linked it again with the reasons. And the more times we turn it around, the more little magnetic fields we link together to make one stronger one. You could have a physically larger plate and electromagnet, which would lead to a larger area to pick up steel. So I've been a bit exhaustive here. Probably 2 reasons, 2 ways to improve it two ways to improve it would get you all the marks. Guys, any questions and things, thank you very much for your comments that are coming in now. It's lovely to see. I will get to questions just after I've gone through these, if that's okay, for the people who are watching this recorded, because that will be the majority of the people who see this. And I need to make sure that this is just a good, quick video for them. All right, so keep tuned. So, next one, at room temperature, this is a circuit basically. A current in a thermistor, which is that one, has a resistance of 1,000 ohms. The current is 2 milliamps. Now actually, my kind of habit would be just to write down the converted version of that, but I'm going to use that in a moment. Calculate the power dissipated in the thermistor. Now whenever you read that, power loss, power dissipated, you're going to use this formula for power. P is I squared R. So here's where I need to use my current and my resistance. Okay, make sure it's converted into SI units, 0.002 amps squared times 1,000 gives me 0.004. So recall the equation, convert correctly and sub in, final answer. Okay, they're the 3 marks. Now, actually, there's 2 ways to do this question, and this is the way that I would do it, and it makes much more sense to me. But they did this in the mark scheme, so I'll go through this one as well, because, well, that's the way they think you should do it, which just seems a bit odd to me. But anyway, let's go through it quickly. So, what's the resistance of the fixed resistor in the circuit? Okay, so basically we're asked to work out this resistance here. So we know some things. We know the current going through the whole thing is 0.002 amps. Now, that's an important thing to do. You've actually already applied Kirchhoff's first law there, that actually current in a series circuit is always the same. So in the same loop, the current through here is the same as the current through there. So that's an important thing to recognize. So in other words, I can work out the total resistance of this pair of resistors here. And remember, in series, resistance is sum. So I can work out the total resistance straight away by knowing that there's 5 volts across the pair and the current through it. So I just use V equals IR, rearrange for the total resistance, V over I, sub in 5 volts, sub in the current, boom. The total resistance is 2,500, okay? Boom, boom. And then I need to recognize that, well, I'm not asked for the total resistance, I'm asked for the resistance of this, no, I'm asked for the resistance of this thing. Okay, so I have to do 2,500, take away 1,000 to give me the final answer of 1,500. Okay, now the way they do it, I think, is a bit strange. Okay, this is not the way I would tackle it, but this is the way that they've done it. They've said, well, look, that's a potential divider. So with what I already know about this, I can work out the voltage across here, and hence I can say that the voltage across here is just whatever's left over. So they've done it like this, V equals IR for the known thermistor. Okay, 0.002 times 1,000 gives us 2 volts across there. So 2 volts across there, that means 3 volts is across this resistor. And then with that, work out the resistance of this resistor by doing, again, R is V over I, and boom, boom. Okay, so obviously, if you get to that answer, you get all 3 marks. There's more than one ways to skin that cat. Okay, don't get me started on skinning cats. Explain how this changes the reading of the voltmeter. Okay, now you need to think about it in terms of being a potential divider. So I guess that's where they were thinking, a potential divider question, that's what I'm going to do there. So the thermistor is cooled. Explain how this changes the reading on the voltmeter. The voltmeter is across the fixed one. So if this is cooled, then this resistance goes up. Okay? Now that means that in a potential divider, so that's my first point to make, and I get a mark for that actually. Resistance on the thermistor increases because it's cooled. So greater share of the voltage is going across the thermistor, okay? Because in potential divider circuits, you get a larger, the voltage is shared out in the ratio of the resistances. So you get a larger voltage across the thermistor, and the voltmeter is connected across the fixed resistor, so you get a smaller voltage here. Okay, I hope that makes sense, just 2 marks there. Okay, police guidance on air rifle states any rifle, blah, 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 16 joules has to have a license. Anything above 16 joules of muzzle energy has to have a license. A paintball gun fires a pellet of 3 times 10 to the minus 3 kilograms at a velocity of 90 meters per second. The license for the gun is not required if the pellet has a kinetic energy of less than 16 joules. Just said the same thing again, haven't they? Use calculation to help justify why a license is not needed. So when you are told that to use a calculation, make sure you do. Just think, what can I calculate here that might be a useful thing? It's probably going to be about the energy, if it's talking about this license and kinetic energy. So bring down the equation, sub in all the numbers, and do the answer. Don't forget to square 90. Kinetic energy is a half mv squared. A half times 3 times 10 to the minus 3 times 90 squared. You don't need to, you're not squaring the whole thing, you're just squaring the 90. So I just want to, again, I want to talk about making sure you can use that times 10 to the minus 3 button on your calculator times 90 squared. Boom. S to D, so 12.15 joules. And then it asks you to justify, so you need to compare with this thing here. So you only get 1 mark for 12.15. You get your second mark for 12.15 is less than 16 joules. Okay, sunlight streaming in, but I think you can still see all right. Give me a thumbs up. Hit the like button if you can still see okay, even with the sun coming in there. Okay, so what's the momentum of the pellet when it leaves the paintball gun? show you working out the unit. Did you remember the equation for momentum? You get a mark for that. Get a mark for putting them in the right place and calculating the right answer. And you get a mark just for the unit. If you ever see that box just like that, it means there is a mark, in this case, for the unit. So if you can remember the unit for momentum, then just go ahead and put it down there, even if you can't do any of the calculation stuff. Okay, next one. The mean force of air resistance on the pellet is 0.26, and it's just the average. Use your answer to part 1 to calculate the horizontal distance travelled by the pellet fired from the gun. Now, there are many ways to do this, okay, and a lot of students are going to spend, if this question came from the exam, they spend a lot of time going through working out the acceleration from this, using the mass, and then going through SUVAT and working out all those different things, okay, working out the time first, and then, the distance, therefore. But you don't need to do that, okay? It's actually a simpler way. Because it's a bit of energy analysis, we're saying basically the kinetic energy it has when it leaves is equal to the work done by this force here in slowing it down. So you just need to recall that the kinetic energy, so you just need to recall that work done is force times distance, and you get a mark for that for realising that's the way to do it. You just calculated the kinetic energy, and it did tell you to use your answer to part 1. Ah, okay. No, it told you to use your answer to part 1, and then it expects you to go ahead and do it by energy analysis. Now, use your answer to part A is what I think they really meant. Okay, is that the way that you should go ahead and do it? Again, so think about that. Is there a simpler way? And kinetic energy analysis is a very simple way to make calculations. So if we know that the kinetic energy is transferred by work, then we can say the work done is force times the distance. So plug in your numbers. This is the force. You want to work out the distance, so rearrange for distance gives you 12.15 over 0.26, which is 46.7. Useful stuff. Okay, lastly, in this question, describe an experiment to calculate the density of the paintball pellet. So they've gone all over the place, haven't they? They've talked about energy, they've done a bit of momentum, they've talked about energy analysis next, okay, and then they've gone ahead and asked you to describe basically a PAG, right? So there's different ways to do this, but firstly, measure the volume, okay, is actually the first mark. Measure the mass is the second mark. You need the equipment that's used. Displacement can or a measuring cylinder would be the obvious thing, okay, and then lastly, you need a balance for the mass. Lastly, you need to use the equation density as mass over volume, and you can write that down there. You could have gone ahead and talked about using some way to measure the diameter and using your circular geometry to give the volume of the spherical pellet. I'm going to move just slightly out of the sunlight. Can you tell me straight away if the stream drops, because I'm moving into a different place and I'm just off the floor. Stream okay? Still nice and healthy? Okay, thank you. So, two beakers are filled with equal masses. Two beakers are filled with equal masses of X and Y at the same temperature. Temperatures of liquids are monitored throughout the experiment. So we're starting up here at this temperature, and temperatures fall in. What's happening to them here, basically, use the graph to compare what happens to liquids X and Y at 55 degrees. So what can we find out from the graph to compare them? Well, they've both taken the same length of time at 55 degrees Celsius. So that is our first point. Both stay at 55 degrees C for the same length of time. However, what's different? Well, X actually gets to be a solid before Y does. So that's the second mark there. And then the last one, we'll compare, it's not just similarities, not just differences, but it's similarities, sorry. So what's happening to them both at 55? They're solidifying. Now, it took me a little while to get to this last one because I was looking at comparing and I was like, well, okay, I've kind of said this, haven't I, about them changing into a solid at this point. But the last one says, suggest what's happening to the liquid at this temperature. So you need to therefore think, well, what's happening to them at this temperature? Was a liquid, now it's going to be a solid at this lower temperature. Okay? A student argues X and Y are the same substance. Well, what evidence is there? They both have the same freezing points. They both turn into a solid at 55 degrees is enough there. Okay, a beaker contains hot water. The pupil wants to calculate the thermal energy lost by the hot water when she puts a cold aluminium block into it. Okay, well, this is recognizing thermal energy lost. Select this equation from your equation sheet. And then what information will she need to make this calculation? Well, she needs the mass, she needs the split heat capacity and the temperature change. But go ahead and make sure you don't just write those things out, make sure you apply them. So we're measuring the thermal energy lost by the hot water. So the specific heat capacity of water, the mass of the water, the temperature change of the water. Okay, so 1, 2, 3 marks for this one. Then the volume of the aluminium cube is this, and its density is this. Calculate the mass of the aluminium and show your working. Again, go ahead. Again, go ahead and rearrange for mass, put the numbers into the calculator, and boom, this is your answer. I hope that before you do anything like that, you just check the units are kilograms, meters cubed, so that you don't make any unit errors. Then last one in this little video, the split heat capacity of aluminium is 0.9 times 10 to the 3 joules per kilogram per degree C. Temperature rise is 5 to 18. Okay, so the first thing you can do is think delta T, so what is the temperature change, and you actually get a mark just for doing that, so that's a nice easy mark to do. It's gone up by 13, you don't use 5, you don't use 18, you use the change in, that's what the delta means. And then calculate the amount of energy, so E is mc delta T. The mass was from the last one, okay, the split heat capacity is from this one here, 13 is delta T, comes out at this in your calculator. 3 sig figs is fine, so using the right equation, selecting the right equation and putting the numbers in is 1 mark, changing temperature is another mark, and lastly, final answer, 257. All right, I hope that helps. I hope that stream was just okay there at the end. I'm just going to have a little look through if there's any questions. You've got your GCSE this week, okay, so do ask, please, if you've got any questions. I'll be back again tomorrow if... Okay, I'll be back tomorrow as well. I'm going to just answer any questions of you for just now. Just turn my camera around so you can see me. Hi, dudes. All right, I will just, not bother to do that. I'll just hold this hand because there's not all that many of you here today. Might be here later on, okay? But I'll just, any questions then ask now and I'll just go through them. So somebody asked, how does a dynamo work? A dynamo is a DC generator, okay, essentially. So a dynamo is a motor backwards. Dynamo is the one that has the slip rings. Okay, hang on, that's wrong. A dynamo is the one that has the split rings because it's a motor backwards. So in a dynamo, every half turn of the kind of block, you are getting the same direction of current in the wire because the overall kind of change is going in the same direction. So you're always getting positive, positive, positive. I hope that kind of makes sense. You need to, when you look at a dynamo, that type of question with dynamos and generators, you need to really get your head around those diagrams that are in the textbook and really just think about the current in a dynamo is changing every half turn, okay, but it's always the same direction in the actual dynamo. The current in the coil is changing every half turn, but it's the same direction out of the dynamo. It's the same connection that it's linking to out of the dynamo. Right, just hopefully that's on a little tripod now. It's going to be a little bit up the nose. You'll forgive me, I'm sure. Yeah, and if you draw a kind of graph of current versus time for a dynamo, you're going to see that they're going to be bumps, but they're all going to be positive bumps. I hope that was okay for a dynamo bit there. Somebody asked about half-life, and that was explained in a kind of A-level sort of way. Half-life's coming up in the next kind of section because that's an OCR paper too. Really easy way to explain it, it's the time taken for half of the nuclei to decay. So all you need to do in a half-life question is identify what the starting value is, half it, use the graph normally to get across to the x-axis where the time will be, and then you can do that's the half-life there. Or if you have to use the half-life to calculate a number that there are, then you have to remember after each time you just half the activity or half the number of nuclei. So you've got to get it that way around. People read it as being, well, a half-life is just what's the value of half them being there. Okay, it's a really simple concept, but it goes into some really deep maths. So if you're struggling to understand half-life, you're probably trying to analyse the maths at a little bit too high a level, because it's quite a simple concept really. If you're in year 10, then it's okay, you've got time to do that. I think that was it. Yes, definitely check out free science lessons, very, very useful thing. Is there a kind of motor that takes an AC current? Not really, Laura. They wouldn't be very useful to us. If we wanted to be able to control a motor using a frequency, that we change the frequency, and that would give us the time period of the oscillation of the motor, that would be a useful thing. But in most cases, we want to just accelerate a motor, so we want to just apply DC to it. And in most devices, well, motors, we want to use DC because they're going to be battery operated, like cars and things like that. So that would be a very much more useful thing for us. Okay, hope that answers your question. And that's me. LDRs and thermistors, how do they work? They're both an application of quantum, which is that basically there's an electron that kind of stuck, and to get them moving across the conductor gap in an LDR or thermistor, they need a little bit of energy from somewhere else. Okay, so where they get the energy from is from thermistors, it's from heat. So you apply a little bit of heat, you get more electrons higher up in the energy bands, and they're more likely to be at that valence band, which makes them available, if you like, to carry current. So LDRs and thermistors. So thermistors is heat, higher heat, raises up the electrons in their energy levels, makes them available to carry the current, so lower resistance. More charge carriers, so lower resistance. And then the LDRs, the same thing happens, but it's by light raising them up in the energy levels, making them available to carry the current. Hope that makes sense. But the GCSE guys, you just need to remember that LDRs and thermistors, higher heat, lower resistance. LDR, higher light intensity, higher light intensity, lower resistance. So really easy one to remember. They're normally going to crop up. In potential divider questions. So it's that kind of question like that one in that set I've just done, where they say to you, well, the LDR changes, the environmental factor changes, and therefore the resistance changes, and you use that to infer how a voltage changes or how an overall current does. Night before the exam, be chill. Okay, night before the exam, don't do questions like I've just gone through. Yeah, sure, watch videos of questions like that, but actually just do some memory work. Make sure you got your equations down. Get yourself to bed. Just, you know, maybe those last few little equations. Go through the kind of set explains. You know, if it was a 6 mark on motors, boom, 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 what would you write? If it was a 6 mark on potential dividers, boom, 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 what would you write? Just go through those kind of little sections that you know come up in those kind of common explains. Make sure you got your equations ready, but don't stress it, because you are not going to suddenly, the night before the exam, learn all of quantum and you know, something brand new that you didn't get a week before. You've just got to focus on the little bits that you normally get wrong and make sure you get those right. So I wouldn't spend a lot of time the day before exam at all. I would just make sure that I was just sort of reassuring myself that I do know these bits, I can do these questions, I'm trained for this, I'm ready to go, and you know, and then just get yourself a nice restful night, get in there at your best and do it. All right, thanks a lot. I'll be back again tomorrow for some more stuff. If you've got any questions there, you can always leave them in the comments if you're watching this later. Okay, there is still time to, probably not to get the paperback, but if you wanted to get a Kindle, How to Memorise Equations for GCSE Physics, then that is linked up below as well, as are more exam questions in playlists for both AQA and OCR. Go ahead and share this out, because really I'm aiming by sort of February next year to get to 10K subscribers. Now, why do I want 10K subscribers particularly? It's because then I get what's called a community tab. And if I get a community tab, then I can start actually just putting out kind of posts rather than just videos. And the post will come through your notifications. And when I go live, I can write a little post and say, oh, I'm coming up live this time. Or I can write a little post to say, here's a video that I found that will really help you guys out. I know you're asking me about radioactivity, half-life, and here's a little thing there. So it'll be a really, really useful tool for me to reach more people. So help me out by sharing this, help me out by saying, have you seen this today? Look, these are the questions that we need to do on Wednesday, okay, and that'd be really useful. All right, thanks a lot, all the best, and I'll see you tomorrow.